So now we're going to talk about plate tectonics, and we're going to do this in two sections. The first section will look at the evidence. How do we know that the Earth's surface is made up of plates that move around and interact? How do we know that? What's the evidence? And so there's a short story that goes along with this, and it actually has to do with the development of accurate maps and charts. So until we get to the early 1800s and we have the ability to determine longitude as well as latitude, it's very difficult to make accurate representations of the Earth's surface. So the shapes of the coastlines, for example, and this is very important to the story of plate tectonics, do not become clear until we get into the mid to late 1800s. If you look at earlier versions of the maps and charts of the ocean, one of the things that's very striking is how oddly shaped some of the continents are. They do not look like we are used to seeing them on modern maps and globes. So that's a big part of the story. People in the late 1800s, early 1900s started to discuss the shape of, in particular, South America and Africa, but really the coastline of the Americas compared to across the Atlantic Ocean, the coastline of Africa and Europe. And when you look at those coastlines, they look like they fit together. And the notable fit really is South America and Africa. And so a group of people who study the Earth, a group of geologists, took a look at that and they said, you know, it really looks like these fit together. If you've ever put together a jigsaw puzzle, use two things. Number one, use the shape. And so that was kind of what initiated this investigation and this question and the curiosity. Why do these things look like they fit? And so you put them together like this, and hey, you say there's actually quite a nice fit. The east coast of the United States looks like it fits snugly along the upper west coast of Africa. And you can see the east coast of South America fits nicely into the southern part of the west coast of Africa. And then if you look up at the fit of Europe in this puzzle, along with Greenland, everything fits together pretty nicely. And you can see the gaps and the overlaps are minimal. So the pieces fit together pretty well. But as with any puzzle, there should be a picture that allows you to confirm that these things actually do belong together. And so what the geologists did was they started to look at the geologic picture, the rocks, the fossils, ancient mountain ranges, which are represented by structures in the rocks, folding and faulting. And they said, do these fit together? And it turns out they actually do. And this is what the picture looks like. Highlighted several things on here. The fossil range of a plant called Glossopteris. There are more plants and animals. You can see a little fossil animal here, Mesosaurus, that goes across the boundary. So when we put things together, we get these fossil ranges crossing over the boundaries. You'll notice up here, North America and Europe, we have this mountain range, an ancient mountain range that kind of connects up across. And there are actually a lot more rocks associated with this. And there are more things geological that cross this boundary. So this is just a highlight of a few of the items. And as I say frequently during this, if you want to know more, take physical geology. We spend 4 weeks looking at plate tectonics and the evidence for it. In terms of oceanography, we're interested ultimately in the implication on the oceans, but we definitely want to talk about the joining of the continents because that's a big part of it. So you can see, in addition to this puzzle that we initially had with the Americas, Europe, and Africa, we've added India, Antarctica, and Australia in here as well. Some other things that cross these boundaries are evidence of past glaciers and other rock types that cross the line. So we've got a really good geologic picture, allowing us to confirm that the continents were together. And so this idea was brought together and investigated and shared in the 1930s. And there were still a lot of questions. For example, how do you move the continents? So if they were together, and it sure looks like they were, how do you get them to move apart? So it would take a lot of energy and force, and there should be some evidence of that. And so essentially what happens in the 1930s is they get to a point where they say we need some more information to kind of build on this idea. At this point, it was called continental drift, and more information was necessary. So what happens next? Well, the 1940s happen next, and we go into World War II. So research on things geological kind of comes to a stop, and instead we spend the next 5 years fighting the war, and then the years after that recovering from the war. However, the war resulted in the collection of information that then becomes data that can be used in the next stage of this process. So we get to the 1950s, and during World War II, one of the big issues was German submarines. And in order to detect submarines, you can use sonar. Sonar bounces sound waves off the ocean floor and back. And if a submarine comes between you and the ocean floor, you're going to get an early return on your sonar. But what's extra important and makes sonar work better is if you know what the ocean floor looks like. So the Navy starts to collect sonar data. Every time ships go back and forth across the ocean, their sonar is on all the time, and then that information comes back to the Navy and they start mapping the ocean floor. The other way that you can detect a submarine is because it's a big hunk of metal, you can look for a magnetic signature. So a metal detector is a magnetometer, and so you can look for a disturbance in the Earth's magnetic field. And so a lot of the naval ships were outfitted with these magnetic detectors, which they had on all the time. And of course, that data also comes back to the United States. And once we get into the 1940s and 50s, researchers start looking at that information that shows them the shape of the ocean floor and also the age of the ocean floor. And when they put all that information together, a couple of things become apparent. Number one is the shape of the ocean floor. And here's what they see. They see that the ocean floor is not like a big bathtub. And we're going to look at this a lot more closely in chapter 4, which is next week, when we look at profile. We're actually going to do some profiles of the ocean basins. But you'll notice there's a mountain range in the middle of the Atlantic Ocean. And at the center of that mountain range, and we call that the Mid-Atlantic Ridge, there's actually like a little rift or a kind of a fracture that runs right down the middle, a little indentation at the very crest of the mountain range. So this is the shape of the ocean floor. They take some samples of the ocean floor, and they find out that it is this igneous rock, which comes from volcanoes. It's very rich in iron and magnesium. And because it has a lot of iron in it, it also has a mineral that we call magnetite in it. And that leads us back to something called paleomagnetism. What becomes very apparent when they look at the ocean floor's magnetism is that some of the ocean floor has a magnetic signature that points in the same direction as the current Earth's magnetic field. For the magnetometer, this gives what we call a positive magnetic anomaly, which means that the little magnetite crystals are all pointing in the direction of the current Earth's magnetic field, which makes sense because as the molten rock cools and solidifies, you would expect those magnetite crystals to line up in that direction. The weird thing is that some of the parts of the ocean floor have magnetite crystals that point in exactly the opposite direction. And what this tells us is that when those rocks cooled and solidified from molten rock, the Earth's magnetic field was pointed in the opposite direction that it's pointing today. Now, what does this mean for us studying the ocean crust? It means that there's some characteristic there that parts of the ocean floor share. And some of the geologists said, you know what, maybe that means that chunk of the ocean floor is all the same age. In fact, if we follow this pattern of magnetism, what we find are actually these stripes of positive and negative magnetic anomalies. Positive meaning they're pointing in the direction of the current magnetic field. Negative meaning they're pointing in the opposite direction of the current magnetic field. What do we do with this? Well, the geologist said maybe they have shared magnetism because they all formed at the same time. And maybe we can use this to determine the age of large sections of ocean floor. Now, what we would have had to do without this magnetic signature is take an enormous number of samples. With the magnetic signature, which represents a hypothesis, hey, we think these are all the same age, we can sample along a magnetic stripe, just take a few samples and see, are they really the same age? And it turns out they are. We can then use those dates to determine the age of all the ocean floor, and in the end we get this map. This is an incredibly important discovery in oceanography, in geology, in plate tectonics, because it shows a really interesting pattern. The youngest ocean crust is found right along the crest of the mid-ocean ridge. And it turns out if you take a submarine down there, you will find underwater volcanoes. There's actually a place where these volcanoes break the surface, and that is the island of Iceland. So that's where we can actually go visit the mid-ocean ridge. There are some smaller islands that do the same thing, but Iceland is notable because of its size. You'll also notice that as you move away from the crest of the mid-ocean ridge, the rocks of the ocean floor get older and older. Not only that, but if you look at this picture, as you get farther away from the mid-ocean ridge, things smooth out. And it turns out that these rocks here, the ocean crust is basically covered with a really thick layer of sediment, which also indicates age, because the longer it sits there, the more sediment is going to accumulate on top of that ocean crust. And so we put all that together, and it appears pretty clearly on this picture that we're making new ocean crust at the mid-ocean ridge. And over time, that new crust moves away, becomes older, and it moves away symmetrically. It moves away on either side. And this is the picture that they show you in the book of what's going on. Up here in the upper left, they show the magnetic stripes that we used to correlate the ages along the ocean floor. And this is how that all happens. We form new ocean crust here in the middle. It pulls apart. One half goes one way, one half goes the other way, and then we continue to add new material in the middle. And this is what we refer to as seafloor spreading. And this ultimately is what leads us to understand what is going on with plate tectonics, which we will discuss further in the next set of slides.